Hello and welcome. My name is Mark Brown. I'm a Principal Program Manager on the Azure Cosmos DB team at Microsoft. Welcome to the session Data Modeling and Partitioning in Azure Cosmos DB, what every relational database user needs to know. In our session today, we'll get familiar with NoSQL concepts, and then we'll also learn NoSQL data modeling best practices and understand how Cosmos DB differs from relational databases, and we'll apply what we're learning here to a real-world scenario. Azure Cosmos DB is Microsoft's NoSQL fully managed database on Azure. When we say NoSQL, what we mean is that Cosmos DB is non-relational and horizontally scalable. So let's talk about the horizontal scale aspects of Cosmos DB. Unless your workload is very small with a low amount of data and request, your data will likely be stored on a number of different physical servers or partitions within something we call a container. Now in Cosmos, we abstract all this away, but under the hood, you're reading and writing data in and out of Cosmos, dealing with a cluster of servers. This is better known as scale-out, and it's how we achieve horizontal scalability, by enabling unlimited storage. So when you need more storage, we simply add more servers to your cluster. This also provides unlimited throughput, as each server adds additional capacity to handle requests when you need it. Cosmos DB is also non-relational. Now, when working with relational databases, you have the ability to define relational constraints between the different entities you're storing. This lets you define things like foreign keys between entity types and perform join operations across these entity types. Non-relational databases like Cosmos DB don't implement these relational constraints. Why? Well, because Cosmos is horizontally scalable, and your data will likely be spread across multiple servers, tens or hundreds, depending on the storage and throughput requirements. Now, I don't want to suggest that it's not technically possible to enforce relational constraints across a cluster of servers, but doing so would have an enormous impact on the performance and availability of your database. And because Cosmos DB is designed to provide predictable performance with SLAs to back it up, Cosmos does not provide a way to declare relational constraints. So, is Cosmos DB okay to use for relational workloads? Well, yes, it definitely is. In fact, most workloads on Cosmos are relational. You just need to learn to use different techniques to implement the relationships between your entities. The approach is very different than designing a data model for a relational database. And for those that are new to this type of database, you do not want to follow your intuitions. Best practices in the relational world don't translate well to this type of database, and may even be anti-patterns. Okay, so let's put this to practice. I'm going to spend the rest of this session taking a relational database that anyone who's used SQL Server should know, the AdventureWorks 2017 database. Well, actually, we're just going to use a small part of it. These tables represent the canonical e-commerce workload. We've got customer, customer address, and customer password. And we've got product, product category, and product tags. And then finally, we have sales order and sales order detail. With a non-relational document database like Cosmos DB, there isn't much we can do with that. You would never use these tables as is because the cost of performance for trying to perform the same operations you need to do would be prohibitive. Another thing I want to point out too is that in a relational database, the relationships between the data are important for modeling the database. For a NoSQL database, these are only part of the story. What is most important when designing a relational model for a NoSQL database is the access patterns for your application. And as I will show you throughout this talk, the design decisions we're going to make rely on these access patterns to the data. A real e-commerce platform would obviously need to implement many more kinds of requests, but this subset is enough to guide our first implementation and illustrate the different design techniques we want to showcase. Here is what our mini e-commerce site will have to do. We have to create a customer, retrieve a customer. We have to create and edit product categories and then list all product categories. We want to create and edit product tags, and then list all product tags. We'll want to create a product and edit products, and then we want to list all products from a category, with the name of the category and the tags. And then finally, we want to create a sales order, list all sales orders for a customer, and then query top 10 customers by the number of sales orders. Okay, so let's get started remodeling this relational database in Cosmos DB. Let's start with the customer entities. We have 3 tables here. First, we will translate each table to a corresponding JSON document. Now, we could keep these in separate containers in Cosmos, but let's look at what operations we need to support. That includes both creating a customer and retrieving a customer. Given that Cosmos DB stores data as JSON, another approach we could take is embed the address and password tables into our customer table. Now, when I create a new customer, I only need to insert data into a single container. Reading data is also easier because I only need to read from a single container as well. So both operations are now both faster and less expensive to execute because I've embedded the data into a single container. So at this point, people often ask, when would you embed data versus when would you reference it? And the rules are actually pretty straightforward. You would embed data when there's a one-to-one relationship, one-to-few relationship, or when related items are queried or updated together. And you would reference when there's a one-to-many relationship, especially if that relationship is unbounded, or if there was a many-to-many relationship, or if the related items are queried or updated independently. Because we have a one-to-one and one-to-few relationship between our entities, and because we usually retrieve all the data corresponding to a customer at once, it makes sense to embed everything in the same JSON document. Now that we've defined our first entity, let's see how we're going to store it. We'll store all customers in a container named customers. But when creating a new container, we also have to define its partition key. Well, what is a partition key? Remember earlier I referred to a Cosmos DB container as an abstraction over a cluster of physical servers. When storing documents in a Cosmos DB container, these documents end up being dispatched to different physical servers. So the question is, how to decide that this document should go to this server and that document to that server? Technically, we're not directly assigning documents to servers. Instead, documents are being written to logical partitions. And it's these logical partitions that happen to sit in different physical servers. And so from a user's perspective, you don't really need to care about physical servers when designing your data model. Just that your data gets written to different logical partitions. So how do I decide which logical partition a document should go to? Well, that's where the partition key comes in. When creating a new Cosmos DB container, you define the container's partition key, which is the name of the property Cosmos DB will use to decide which logical partition your data should go to. Think of it as an address to route your data. Using the example of a container partitioned by username, we would end up with a logical partition with data where username equals Andrew, a second logical partition with data where username equals Deborah, and so on. There are 2 constraints to keep in mind when designing your data model on Cosmos DB. First, each document has a maximum size of 2 megabytes. Remember before when I talked about when to embed or reference? It's because each document can be no larger than 2 megabytes, which is why you don't want unbounded arrays in your documents. Also, each logical partition has a maximum size of 20 gigs, so you can't have more than 20 gigabytes of documents where username equals Andrew. When working with data, we want to strive to achieve an even distribution of data across different logical partitions. If one partition gets a lot more data stored on it than others, this is what we call a hot partition, and we want to avoid that. Same goes for the request as well. If all or most of your requests hit the same logical partition, this is going to be a bottleneck that will drastically limit the overall scalability of your model. We want to end up with a design where storage and throughput are more or less evenly distributed across our different logical partitions. So the partition key plays an important role to performance and scalability. Let's take that example of a container partitioned by username. If we were to issue this SQL query, you'd notice that it filters on the username property, which is our partition key. And because Cosmos DB understands that, it will send this query to a single partition. This means that the query will always hit one single physical server, so its performance will always be good. If our query filtered on something else, like favorite color here, we would have no idea where the actual results are. So in this case, Cosmos DB fans out the query to each and every logical partition of your container. And as you've probably guessed, this is going to hit each of the underlying physical servers. This is what we call a cross-partition query. Such a query will work, but it will have an impact on the latency, throughput cost, and scalability of your application. Now, for small containers, this performance impact is not that bad. However, as your database grows larger, the impact becomes worse and worse, as you have to hit more and more servers to answer your query. Now, with all that knowledge about partitioning, how do we choose the right partition key for customers? Remember before when I showed the operations we needed to do for customers? We had to do two things. We need to create a customer, and we also need to retrieve a customer. In this case, we'll do that by ID. So the ID of the JSON documents we're going to store in this container should make for a suitable partition key. Note that when using the ID as the partition key, we end up with as many logical partitions as there are documents in the container, with each partition containing just one document. And that's perfectly fine. Many users are concerned about having a very high number of logical partitions, but no need to worry. Logical partitions are a virtual concept. Cosmos DB co-locates logical partitions on the same physical servers and moves them to different physical servers when needed. And there's no upper limit to how many logical partitions you can have in a container. Okay, let's do a demo. In this demo, I'll show you a query for a customer by ID and then return that customer's data. Okay, so here we are in our demo application. I've got my endpoint URI, my primary key, and a static Cosmos client that I'm going to keep alive for the life of my application here. First, we're going to query customer. So I'll get a reference to my database and my container. I have a customer ID here, and then next I have my query. Select star from C, where CID equals @ID, and then I'm going to create my query definition, pass in a parameter, and then I'm going to specify the partition key for the customer ID here. Then I'll run my query and then print out the results. So let's run this application here, query for a single customer. And then here you see the first and the last name, the address or email address, phone number, and then address as an array because I can store multiple addresses in this customer. And then here's the password. And the request charge on that is 2.83. Now, another thing I wanted to show you is if you're looking up just a single item, there's actually a faster and cheaper way of doing it, and that's called a point read. So here, I'm looking up the same customer ID, but instead of writing a query, I'm going to call read item async, and then just pass in the ID of the customer, and then the customer ID and the partition key, and then I'll just print that out. So let me show you that. So here, I got the same customer coming back, same data, but you'll see that the point read has an RU charge of just 1. And so in Cosmos DB, anything you do a point read on that's a kilobyte of data or less will always cost you just 1 RU. Okay, let's go back to our slides. Okay, next let's look at the product tables. And first up is product categories. We'll do the same thing we did earlier, which is translating the entity into a JSON document. And we will store that document in a new container called product categories. Next, we need to figure out what its partition key should be. Again, we'll look at the request we need to support in our app. Here we need to create a product category and edit a category. We also need to list all product categories. One thing I wanted to point out here is when looking at operations you need to support, it's important to know the volume of those operations as well. For instance, creating and editing product categories doesn't happen very often, but the query to list all product categories probably happens very frequently. There's another issue here as well, and that is there's no where filter on this query. So how do we make this a single partition query? Well, the answer is to use a little trick we can apply here and create a new property and give it a constant value in our document. Here, I've created a property called type and then given it a value of category. Now I can partition by this type property and set its value to category in each document. I'm sure you think this is ridiculous and looks a little bit weird, but later on I'm going to iterate on this design and you'll see how this actually makes sense. Okay, so in this demo I'll show you the query for product categories and we'll measure its RU charge in our app. Okay, so we'll look at list all product categories here. And I'll get a reference to my database and my container. And then in our query is select star from C, where C type equals category. I'm going to create my query definition and then pass in the value category for my partition key. And then we'll loop through the results and print them out. And here we see all the results for all the product categories coming out of our database. There's about 37 of these. And our request charge is just a little less than 4. So a pretty efficient query. Okay, next let's look at the product tags. I'll apply the same process here to product tags by defining a JSON document. And we'll store tags in its own container called product tags. Now it turns out that tags actually share the same exact access patterns as categories. So we'll just go ahead and apply the same strategy here. And we'll partition the container by type and set its value to tag for each document. Okay, next let's look at the product table. First, I'll translate my schema to JSON. Next, I want to look at the relationship to the product tags table. Our product table here has a many-to-many relationship with tags. I need to access tags, the product tags, in my application, meaning that I need to display a product and then I need to display the tags to appear as well. I also need to be able to query for product using tags. Now, I could do this one of two ways. I could store the product info in the product tags table, or I could materialize the tags in my product table. Now, given that there are much fewer tags per product than products per tags, it makes more sense to materialize the product tags and embed them in my product table. Remember too that there is a one-to-few relationship between product and tags, so this too makes it a good candidate for embedding. Next, we will store our products in their own container named products. Next, let's figure out a good partition key. Again, we will look at the operations we need to perform and decide on a partition key. We of course need to create and edit a product, but the interesting operation is querying for product by category. This is likely how customers will search for products. We need to list all the products that match a specific category, so the corresponding SQL query is select star from C where C.categoryID equals category A. This will return all products for that category. In order to make this a single partition query, we would need to have all products from the same category sit in the same logical partition. So category ID is a good partition key here, as it will allow us to retrieve all products in a category very efficiently. But now the problem is that every time I query for products in that category, I get a category ID and a bunch of tag IDs. What I really need to do is display the category name and a list of tag names in each product. In order to achieve that, I would need to first run my query that I defined on products, then issue a second query on my product categories container to retrieve the name of the category, and then for each product returned, issue multiple queries to fetch the corresponding tag names. Now, this could work, but it's not very scalable, and you may be asking yourself, well, hey, why not just use joins? Well, as I mentioned previously, Cosmos DB is a non-relational data store. It doesn't support joins across containers. Data that is modeled in this type of data store is optimized such that it could be served in a single request. So, to our products table, we are going to add additional properties, including the name of the category and the name of each of the tags. By doing this, we make sure that we can retrieve all the data we eventually need to return to the clients in just one request. Okay, so let's see what this looks like when we add the category and tag names into our products container. Okay, so I'm going to run this function here, query products by category ID, and we'll get a reference to our product container here. And then I've got the category ID, and this category name is components, headsets. We'll then query for products by the category ID. So select star from C where C.categoryID equals @categoryID. We'll create our query definition below, pass in the parameter for category ID, and pass it in for the partition key. We'll then loop through those and then see all the products in our product container for that category. And here you can see I've got 3 products that come back, all on the components and headsets category here. And a request charge of just a little less than 3. So now when we create a new product, we need to populate these additional properties. But what if we rename a category or a tag? How do we manage that referential integrity between containers? Well, as it turns out, Cosmos DB has a way to handle that. And it's called change feed. Change feed is an API that lives within every Cosmos DB container. Whenever any data is written to Cosmos DB, such as an insert or update, change feed streams these changes to an API that you can listen to and then use that event to respond to the data that was changed. So in our case, we will have to listen to changes that occur on the product category container as well as the product tag container. And every time data is updated, we'll also need to propagate that change to the product container accordingly. So in this demo, I'm going to show you how to use change feed to do this. First, I'll query the product container for a specific category, and we'll see how many products are in that category that need to get updated. I'll then update that category's name in the product category container, and then show how we use change feed to capture those changes and then propagate them to every product for that category in the product container. So first I'm going to do is query products for category. So I'm going to get a reference to my product container here, and here's the category ID that I'm going to search for, and that's accessories, tires, and tubes. I'm then going to do a count to see how many products in the product table are in this category. So we'll just create a count, call that product count with the category name, and then do a group by on the category name. And then create our query definition, pass in the category ID for our partition key, and then we'll print out the results. Next, we'll run an update on the product category. So same category ID again here. And then what we're going to do is create a new product category object, pass in the category ID. Of course, we're going to call that type category. And then we'll update the name slightly, and we'll just replace the and with an ampersand right here. And then we're going to call this function, replace item async. This is how you do an update for data in Cosmos DB. And you pass in 3 things. You pass in the partition key, the ID, and then the item itself. Okay. Next, we're going to show you the change feed. So here I've got my change feed. And what to point out here is I want to have a category to listen on, that's the product category. And then I'm going to have a destination container here as well, or excuse me, product category container. And then my product container is the container I'm going to do something to. So I'm going to listen to this one and then do something in this one here. So within this function here, you can see I'm just getting the references to my containers and then my destination container here. And then I'm going to create a lease. I have a lease container here as well. This is like a checkpoint on change feed. And then in here is where I define what the change feed is listening for and then what I'm going to do. So as changes come in, they come in on this input object here. And then I iterate through that and grab the category ID and the updated name. And then I'm going to call a function here each time a change comes into product category. And I'm going to call update product category name. I'll pass in the destination container, the category ID, and then the updated category name. And then in that function lower here, let me open this up. What we'll do is I'm going to run this query here. And then in the result set, I'm going to loop through every product and then update the category name for that product, and then call replace item async again to update the product within the container. Okay, so let's go ahead and run this. And here you can see I've got 11 products in my product container with this category, accessories, tires, and tubes. And next, I want to bring in my change feed processor, which I've started right here. And then, oops. Now we're going to update that category, and then we'll keep an eye, and then you can see one change received. And we've updated all 11 products with the category name updated here to now include the ampersand. So let's query our products container again. And now you can see, yep, 11 products with the new updated category name. And what we'll do is we'll change it back so you can see that one more time, and then change feed here below should show up, one change received, and it's updated the 11 products back to the original name. Okay, we're now on to our last entity, sales orders. Same process as before. We'll start by creating the JSON for each entity. This is obviously another good candidate for embedding because it's a one-to-few relationship. And it also makes sense to embed the details with the sales order so we can query for the entire order with just a single efficient point read. And next, we'll store sales order in a container called sales orders. So let's look again at the expected operations to decide on the partition key. So of course, we need to create a new sales order, and we need to list all sales orders for a customer. Let's look at this first query. Select star from C where C.customer_ID equals customer A. So to make sure this is a single partition query, we would need all sales orders for a customer to sit in the same logical partition. So we'll make customer ID our partition key here. Before we go any further, let's take a step back. When looking at containers we've defined so far, it's interesting to note that we already have a container that is partitioned by customer ID, and that's the customers container. So could we store customers and sales orders in the same container? The answer is definitely yes. Not only is this technically possible, it's a best practice for a NoSQL database. Cosmos DB is schema agnostic, so this is something that is totally supported. And it's suitable when data share similar access patterns and share the same partition key. So instead of storing customers and sales orders in different containers, I'm going to put them in the customers container. I'm also going to change the partition key from ID to customer ID, and I'll add customer ID as a property to each customer document. Customer documents will now have the same value for ID and the new customer ID property. Next, to help distinguish the sales order and the customer entities within our container, I'll add an additional type property that has a value of customer and sales order for each entity. This way, I can query for each separately if I want. Okay, so now what we have is a customers container where each logical partition will contain exactly one customer and all that customer's sales orders. So now, to get all the sales orders for a customer, we simply run with this updated query here. Select star from C where C.customer_ID equals customer A and C.type equals sales order. Okay, so now let's see what that looks like. Back in our demo app here, I'm going to run this function, query sales orders by customer ID. So we'll get a reference to our customer container now, and then here's my customer ID, and then my query. Select star from C where C.type equals sales order and C.customer_ID equals @customer ID. Create my query definition here, pass in my parameter, and then my customer ID is my partition key, and then we'll run the query and then print out the results. And here you can see I've got 2 sales orders for this customer. Finally, let's look at the last request we need to serve. We want to query our top 10 customers based upon the number of sales orders they've had. This requires you to count the number of sales orders for each customer, then sort these counts in descending order, and then return the first 10 corresponding customers. Even though customers and sales orders sit in the same container, this is not something you can currently do with Cosmos DB's query language. Once again, the solution is to denormalize. This time, we're going to denormalize the count of sales orders in the customer entity. So now what we want to achieve is that every time we add a sales order, we also update the corresponding customer document to increment its count of sales orders. Here we can benefit from the fact that each customer and their sales orders sit in the same logical partition. Cosmos DB supports transactions for data sitting in the same logical partition. So these 2 operations can be performed in a transaction with either a stored procedure or using a new feature in our SDK called transactional batch. And so our last request can now be served with this query. Select star from C where C.type equals customer, order by C.salesorderCount in descending order. Okay, our last demo. In this demo, I'll show you how you can maintain an aggregate for sales orders in the customer record when a new order is created. I'll also then show you how to query for the top 10 customers. Okay, so we're going to run a couple of functions here in this demo. We're going to run query customer and sales orders by customer ID. Here we'll get a reference to our customer container, and then here's our customer ID. This is the same one we had as before. And then here's our query. Select star from C where C.customerID equals @customerID. Now notice here, I'm not filtering by type. I'm going to get back, in fact, one customer record and then all of their orders. So my query definition is going to be a little bit different, and then I'm going to use a dynamic type rather than typing it to a customer or a sales order because I'm getting both types back. What I'll do is I'll create a customer object here and then a sales order as a list. And then as I loop through my results, I'm going to check the type in the response here, item.type equals customer, and then I'll deserialize the customer object into that. And then if I see item type equals sales order, I'll then call orders.add and then add the deserialized sales order to that. And then we'll print out the customer and then print out each of their sales orders. So let's go ahead and do that. Okay, and here I get back my customer object here and their address and both of the orders. And you'll notice here, sales order count of 2. Next, we're going to create a new order and then update the customer order total. So here, get a reference to my customer container again. And then I'm pulling back the customer record itself. So I'm going to do a point read item async, pass in the customer ID, and then as the partition key, pass in the customer ID. And then I'm going to save that in my customer object here. Next, I'll increment the sales order total here, so customer.salesorderCount++. Next, I'm going to create a new sales order. So I've got a new sales order object here with all the details filled in from the products table. And then next, I'll execute these as a transactional batch using this new function, create transactional batch. Pass in the partition key, which is our customer ID, of course, and then I'll call create item on the sales order, and then replace item on the customer, passing in the customer ID and the updated customer object with the increased sales order total, and then execute that. So let's go and do that. So I'm going to create a new order and update order total. Okay. New order created successfully. Now, let's go back and run that function again, query for customers and all orders, and let's just see what happened. So here's our customer record, and here you go. So sales order count is now 3, and I've got my first 2 sales orders and our new sales order here. So what happens if, say, the customer wants to delete an order or wants to return it? Well, it works the same way. I'm going to get my customer object with a point read, and then I'm going to decrement the sales order count, and then I'm going to call create transactional batch. And this time I'm going to call delete item, pass in my order ID, and then replace item on my customer object. So let's try that. Okay, order deleted successfully. And now let's query for our customer. And here you can see our customer object and sales order count is back to 2. And then here you see our first 2 original sales orders for this customer. Okay, last query. Here we're going to get our top 10 customers. So get a reference to my customer container, and then here's our query. Select top 10 C.firstname, C.lastname, C.salesorderCount from C, where C type equals customer, order by C.salesorderCount in descending order. And we'll then just go and then run that query and loop through the results and then print it out. So let's go ahead and run that. So we'll run query top 10 customers. And here you can see our top 10 customers here returned in descending order with a request charge of 13.08. I don't know if you noticed, but that last query was a cross-partition query. Remember before I said you want to try to avoid these, but in reality, they're okay for operations like this that aren't run very frequently. It's also important to keep in mind that it's not necessary to make every query a single partition query. This is both not practical and often does not save enough money to pursue. When analyzing your access patterns, the key is to ensure that those operations that are run most frequently are the ones you want to focus on. Queries like this one that may get run like once a month are not a big deal. Okay, so we're nearly at the end remodeling our database. So far, we've created the following containers to support our design for our e-commerce application. We have a customers container that contains both customers and sales order entities. We have a products container that contains products and denormalized product category and product tags. And we have a container each for product category and product tags. But there's one more place where we can optimize even further. Notice that both the product category and product tags share the same partition key. And as you may have guessed, because they share that same partition key, we can just group them together in the same container, which we then rename to product meta. Okay, well, I hope you've enjoyed this session. Key takeaways I hope you run away with today is always start by looking at the access patterns for your data and design around the most important and used operations. Partitioning is absolutely critical to achieving optimal performance and scale. A container with a good partition strategy will both provide the same performance and latency, good performance and latency, regardless of size. You want to materialize the relationships for your entities by either embedding them, denormalizing and aggregating, and storing related entities together. Finally, you want to use the tools built into Cosmos DB itself to manage the denormalization, including change feeds, stored procedures, or even better, transactional batch. So, if you're interested in getting the demos you saw today, as well as the data and resources to try this yourself, feel free to check out the link here at the top on GitHub. The second link here is for an article that goes through some of what I showed here today, but uses a blog platform as the use case. Also, definitely check out all our awesome videos out on YouTube. And finally, gotcosmos.com, which has links to a lot of great content as well as our blog. And that's it. Thank you very much for joining me. I will take your questions now. Thank you again.